recording. Okay, so today my syllabus calls for talking about how to build a mousetrap car that is satisfactory. I would have handed you a note on what we're looking for. I think I need to change out the dates on this guy before I send it to y'all. But the general idea is that we are going to have a car powered by a mousetrap. This was not a good choice here, this one. Somebody was trying to be cheap, and it didn't go very well. This guy here is mine, and let me just say it's doing better than it did better than I expected it to. And I'll probably use it again for this one. So, what in the Sam Hill are we doing with the mousetrap car? So, alright. So, there's some stuff we haven't talked about just yet. I think today would be an excellent day to talk about those things. We have that. So, we are going to, before we get into an actual mousetrap car, the point of a mousetrap, or its mousetrap car, is that we have a mousetrap like so, and put in our little wire here, so normally the wire comes over this way, but we are going to store some energy into that wire, into the spring here, by bringing this guy here. And so we're going to, by moving it this way, we have now done some work. Work is done, and energy is stored. If it's spelled right, stored. Okay, so what samples are these little bits here? Work is equal to force times. Somebody needs in. Yep. Come here. Come here. I would like to add. There we are. There we go. And I think that can get rid of that now. There we go. That's a little better. So some work is done, some energy is stored, and the work done is equal to force times displacement. So obviously if no work is done, then if no force is applied, then no work is done. But if nothing moves, yeah, it feels like you're doing work. So if you go to a wall, apply some force to the wall, you wear yourself out trying to push the wall over, but the wall doesn't move, and it feels like you've done some work, but no work has actually happened. And so what's actually going on is that the muscles in your arms and the rest of you are trying to push on the wall, but they can't continuously push, and so they're letting go, and they push and let go, push and let go. You feel like you're applying a continuous force to that wall, but you're not. You're applying your parts, the cells of your muscles are applying a force and letting go, applying a force and letting go, and so in the process of doing that, you're doing some work inside of you, and so you're wearing yourself out. Force is applied. This guy comes over. Nice displacement, and so some work has been done, and then we have now stored some energy into the spring here, and so we actually now have a potential energy in the spring. Potential energy is 1/2 kx squared. There's some rotational thoughts about change. There's some ways to properly turn this into a rotational thought for the fact that we're doing things rotationally, but more or less mathematically these are sufficient to our purposes. So we have stored some potential energy into the spring using this guy, and then energy is conserved, sort of. um, energy is conserved so the potential energy that we have stored now turns into potential energy now becomes so when you let this guy go, brings back the other way, your potential energy turns into a kinetic energy equal to 1/2 mv squared. And so what we want to do is instead of just letting the mousetrap snap back, we want to take that energy and put it into something else, make that work out. Well, how do you do that? Well, most of that is what we talked about there on Wednesday, or was what I talked about on Wednesday, where we used simple machines. We use simple machines to turn PE into KE in a controlled manner. Okay. So, what can we do about that? Well, we have several. There are, I think, the most useful ways of achieving that is to do levers and pulleys. Levers, pulleys, wheels, and axles. Those are going to be the things that are most useful to that end. So we have the way the mousetrap itself works is you have the base plate here. You have this pivot here. So this is actually going to work as our technically speaking, this is going to be our fulcrum here. Fulcrum, if I spell it right. Fulcrum goes there, and then we have our lever arm comes up this way, and the spring comes along here, and it basically applies all along here a force. And so I think the best way to put it probably about here. So we have a force come back this way, which that'll be our force spring. And then so now we can do several possibilities. This is normal length of our mousetrap of the mousetrap wire here, and so you can take off of this guy. You can bolt to it. You're going to affix to it some way or another. I recommend what I ended up doing on mine was some combination of hot glue and wire. Right? Yeah, hot glue and wire. So we got some wire going around here, a little wire around here, and a big old dollop of hot glue there, and a hot glue dollop here. As the mousetrap ends at that point there, right? And so you make it a little bit longer. So now I have a and so now I'm going to have a force coming back this way for the tension into a going into a string, going back that way. Okay, that works. That's not too bad. That's a good start. We are using a lever here. Lever to reduce the force in question. Reduce the force, and we're going to extend the distance traveled. Okay, well, that's all lovely and good. Another way we could make this work a little better. I don't care about that. We could also use a, let's see here. Well, we're going to apply. We need to affix our mousetrap to a bed of some sort, right? So we got the mousetrap and this guy here, and we're going to have some amount of distance. Well, in this case, we're going to need to we're going to need to fix it to not bed. We're going to fix it to a frame, right? And that frame will have in it wheels. So got this guy here, got a nice big little wheel around that one. And we have this guy over here. We have a wheel over in here. And so when our spring is over here, like so, we can now put into here a string that goes around this wheel here. So when this guy comes out, goes that way, and now I can pull this guy around and go around this way. And so what I'm doing here is changing colors. Let's go grab the red one. We're going to basically have a lever arm that goes from here for the string and turn it into the wheel here. So I have an R axle there and an R wheel there. Alright, let me turn it back to black. And so then we end up with some more mechanical. Basically, there's too much force There's too much force in the mousetrap itself, and so we're applying some mechanical disadvantage to reduce the force coming out of here, so that your force coming out of your wheel, the force of the wheel over the force at the axle, well, that's going to be equal to the radius of the axle divided by the radius of the wheel. And so this will be your mechanical, technically speaking, mechanical advantage. But if it's if I in the general sense, this would be a mechanical advantage. But we're trying to slow it down, so this is going to be less than 1. So this will be less than, right? Yeah. So it'll be less than 1, which makes it a mechanical disadvantage. All right. Well, so. All right. Well, there are other ways to make things work. It is not necessary to gear the mousetrap all the way down. Quotation marks on all the way. Whereas Samuel, that's supposed to mean, right? When I was in high school, I think I was a junior at the time. I took physics, I think, as a junior in high school, and Mr. Farden had us also do mousetrap cars, and I thought I would be, clever cogs and try to gear this thing down as far as I could possibly make it go, and so I ended up with this lever arm of about it's getting close to a meter in size, meter in length. And I tied that down around my axle, and the axle into some CDs, and so I got a little more out of that. And I thought, this will work, no problems. That's a problem. I managed to gear it down so far that I didn't have enough torque to make it go anywhere. And that was, shall I say, disappointing. So it would be wise to not overdo this mechanical advantage here. In fact, I don't think you need to go way down, but you definitely need to go down some, because if you don't go down enough, you will need to. Hold on. Let me move these guys around. So here, come on, come here. There we go. Your mechanical advantage. Needs to be small enough. Needs to be small enough so that your output force, your force out, is less than your static force of friction. It has to be less than the friction that you can get off these wheels here. The task of the mousetrap car is there are a variety of competitions for mousetrap cars. I like keeping this one simple. We are interested in distance. We wish to we want to maximize our distance here. Which means we want to convert all PE into KE, and then want to coast. We want to do this as quickly as possible, but we don't want to be if we do it too much, so if our force out is greater than if the force out exceeds the force of friction, then the wheels will skid. And just here, so force out have to be greater than force of friction, then the wheels will skid, and we lose. Oops. We end up losing. Losing PE to KE conversion here. That's actually a problem with my car. Let's see here. Then pull back to Firefox here. I would like to stop that. Yeah, stop presenting for a hot minute here. Can I make myself the big one? No, that's not what I want. Reframe? No. I show phone videos to others as well. See a full uncropped video. Others will call. Displays all calls until you turn off. Okay, that sounds great. Nope, that didn't work. Well, maybe we'll find out. Well, that's not quite going the way I want it to, because I'm filming this screen and now I'm a little shorter. Anyways, so this is my car here, and so it's all the red stuff is 3D printed, and so this is plastic here, PLA, and it doesn't have a lot of friction on it with it to the ground, and so what happens is this will spin like so. Well, if the string doesn't bind on it, it'll spin on the ground, and then because it's not quite perfect circle here, it's a bit of a it has straight edges here. This will actually bounce off the ground a little bit, and it's plastic, so there's not, and we're on tile, so between plastic and tile, the force of friction is kind of rubbish, and so it'll spin out, and so I'm missing, I don't know, half or more of the energy I stored in my mousetrap, and so I don't get all of the energy that I stored, and so I don't go as far as I could. Go away. So that. Thank you. All right. It keeps distracting me about email messages. I was like, yes, I know. The snow. Yes, I'm aware. So what else can we do here? Okay. So, where's my? Okay. Go back to sharing my. Allow. Grab that. This one. Yeah. Grab that. Like so. So there's two ways we can increase the friction and make sure that we don't have that one. I don't care. Is it there? So we want to increase the amount of friction in our drive wheel. And there's two ways you can do that. You can, so you need to increase you need to increase the force of friction. Force of friction is equal to mu times the force normal. And the force normal is equal to the weight. So the weight is mg, so this turns into mu mg. G, you can't change that. You're not changing G. You can't make it. You can't increase friction by increasing gravity. You are on Earth. You're stuck on Earth. We're not moving anywhere. We're not going to Jupiter. G is what it is. But we can change the mass, and we can change the mu. So obviously, mass. We know what mass is. You just increase it. Mu here. The mu is the coefficient of friction. Coefficient of friction here. So coefficient of friction is based on materials. Materials based. You can't change out the. If you could change out the materials of the tire, of the wheel, of the driving wheel, and you might want to change out the material, the track you're running on. Unfortunately, we are stuck with the material I will grant you, which is the it will be the tile. Not tile. I think it's stone. It's gonna be the first floor hallway in Farrell, and I think that's a stone of some flavor in there. So whatever it is, it's what that is. Tile or stone, whatever it is, they're about the same. But what we can do is make a wheel by whatever means you want, 3D print it or get a CD or what have you, and then get a balloon, and so you can replace the rim with something different. So you could say make the rim become, say, rubber. Make it a rubber balloon or something like that. And in that case, now you have increased your coefficient of friction, and now you can get more force out of your wheels there, which is really handy for making it go faster. So what you want, one of the things you want to do is you want to, so another thing you could do is it would be advantageous to increase your force out so that you can coast it longer. If you let out the energy slowly, then when you get done, when the all the energy is out of your mousetrap, your velocity is not very high, so that means you won't go much further past the exhaustion of your mousetrap, and so you won't add any more bonus distance to that. So you can increase your coast distance by increasing your velocity at the time of exhaustion of your mousetrap, and so to do that, you want to increase the force out if at all possible. But you don't want to exceed the force of friction. So yeah, you need to torque it. You need to run it through your simple machine to reduce your force out below the force of friction. But you want to increase your force of friction up higher so you can get it to go faster, so that when the string runs out and when the mousetrap runs out, you will let it coast further, and so you get your distance to go higher. These are tips and recommendations for a classic mousetrap car. If you want to involve gears in there, you go around ahead. More gears meaning more friction in your inside the car means that friction will eat the work coming out of your spring and prevent it turning into your kinetic energy. So you want to keep the mechanism for turning PE into KE, your potential energy into kinetic energy, as simple as possible so that you aren't eating it in friction. That would be disadvantageous. What else is in here? I think those are the main points for making good making good mousetrap cars. You also have to be concerned about. There are alternative solutions. Let's see what I want to get rid of. I would like to get rid of. Let's see. I have heard tale of students being particularly creative with their mousetrap cars. It is not necessary that your car be in the shape of a car. It is possible, if you are so inclined, you could just take. Go on. Go on. You could just take the mousetrap here, elevate it up a bit. So I got the base here. And then extend this out a bit, like so. And then put your wheel here. And just have it. You could just catapult your wheel. That is also perfectly valid. It falls within the rules I have set. However, what you don't have in this case is control. I believe, if my memory serves, I said I believe, one moment. Oh yeah, I'm gonna keep that rule. I like that. It is possible in this case that instead of going forward, it goes backwards. Well, it won't look like that. It'll probably look more like this, off going this way. And so I have said in here, it is make sure that your device always travels forwards. It is possible to score negative displacement. So if you meant to go this way and you ended up going that way, that would be bad. And so this becomes, instead of a positive displacement, it becomes a negative displacement. And you don't want to do that. So if you want to do a catapult and catapult an axle, well, that's probably not the. Actually, this doesn't fit within my rules. It may be possible to make something to catapult something that satisfies the rules, but this is not it. The rules specify. So let me read the whole rules here. Mousetrap car. Design and build a vehicle that is powered by a mousetrap. The vehicle can only be powered by the provisioned mousetrap, which I will provide to you on Monday, assuming nothing weird happens. You'll provision all of the materials, keep track of the build materials, and the cost of the build. You may use the department's 3D printer. to produce vehicle parts. The charge to your bill of materials will be 1.34 cents per gram filament. We do not charge students for use of department materials for classwork. The vehicle, so here's the important bit, the vehicle will have at least 3 wheels distributed across 2 axles. So this guy works here, but a single axle with 2 wheels does not qualify. So this is not a good design here. It may be possible that you could get a tricycle that looks like this guy, and it may be possible to get your mousetrap to launch that. It may be possible that could work. I don't think it will, but if you have experiments showing that will work, you go right on ahead and try to catapult your vehicle. So on Monday, I'm looking for designs of the vehicle with material specifications. For designs here, let's see here. Anything else in particular that come to mind? I think that's about, yeah. Is anything else floating around in my head about these guys? Yeah, I think that's about it. So we'll get rid of there. Come here. Come here. Oh, one more. Delete that. There we go. I heard it's something. Oh. Okay. I don't see any notifications here. Okay. Flip back to where I was making things. So, yes. This is individual work. You can share ideas on how to make things better, but you'll be providing your own design, and you'll be making your own car. So on Monday, what I would like to see is I would like to have a design. Whatever, with top, side, and front view. So let me show you little things in drafting stuff, and specifying my own car here. So I have a small front wheel. That's a little too small. There we go. I have a small front wheel. I have some bigger back wheels. In between the two, I have a frame like so. And then in between them, I'm going to put I got my mouse trap in here. And I'm going to put my drive wheel over this way. So now I'll go straight down to here. Got an axle there, got an axle there. So it looks like this from the side. And then on top, so I got a wheel here. I got 2 back wheels here. A little bit bigger. Back wheels like here. And then got the axle there. And then the frame goes back like so. And then the axle comes across through here, and then I have my mouse trap in here, and then the arm goes back there. Actually, that's not how that's technically done. The lever arm on my mouse trap is here, and then it's on the other side, on this side here. I have my dowel that comes back to here. Like so, something like that. So there's my top side. So the side, top, and then we get clever with our come here. We get clever with geometry, and so over here I put a 45-degree mirror here, and if you needed to, top comes down here. I believe this will work. I'm trying to remember exactly the details, what's going on. And then this guy comes over here. Uh-oh, I think I went backwards. Hold on. Back it up just a bit. I think I need to project it up. I think I need to go this way. Oh, that's gonna be way over there. It's been a hot minute since I've drafted anything properly. There's our 45 degrees. Axis comes here. And that guy goes up this way. There we go. And then this guy comes over here. And then he bounces off this way. There we go. And then the top of the wheel comes this way. And the top of the wheel is over here. So now I know that my wheel is here, and my wheel goes here, and then the other one, the middle one, goes up to here through the middle, and up this way, and then I can trace over here, and then I know that I have a wheel about yay big here, and then got an axle that goes there and an axle that goes here, and so now I know my frame comes down here like so, and I got a frame over here like so, and then I have the mousetrap itself fills in this spot into here. Actually, I'm going to change out the color on that. Keep that. Keep that one. Change out the color. Let's go with red again. So we'll put that. I'm going to change this guy out to red. Quotation marks and change. So there's my mousetrap car. The mousetrap itself. Come on. Mousetrap is there. Comes up this way. Mousetrap goes there. There we are. And then I know that in here. Let's go ahead and fill that in just a little bit. There we go. Try to not wipe out the dowel itself and all the detail there. There's my mousetrap in red, like so. And now I can put my mousetrap here. And then I can grab, turn it to black, turn to brown. Let's turn to brown. Brown is a dark orange here. There's the orange, and then I need it to go dark on me. Brown is, there we go. There's brown. Let's make that dowel brown. There we go. We got the dowel. And the axles here are also made out of wood, so we'll go ahead and color those brown. Alright. Come here. There we are. And so we've got the axle right here, brown dowel, and this axle over here is another brown dowel, and I think I'm going to have this side here. The brown dowel coming off the mousetrap goes here, and then the string comes down to the back axle there. And so here we have it. We have, flip it over to black. There we are. So this is our side, top, and front view of what we've got going on here. Typically speaking, if you're drafting out properly, top would be up here, side be down here, and then you have to bring the front and put it over here instead. Yeah, so that's what I thought I was doing, and it turns out that's not what I was doing. So this is basically what we're looking for. So we are looking for this guy. So we're looking for a drawing like this, and brown is a dowel. red is the mousetrap, and black is it's a 3D print PLA. And so this is what my car is going to be. Part of what's going to happen here is that I am going to enter my car here, and you'll be judged on 4 criteria. Mousetrap will be judged on displacement traveled across level ground in the designated direction. Displacement per gram, displacement per dollar, and faithfulness to the original design here. See our design turns out on Monday, and then next travel. We are only interested in travel going forward, not to left or right. So that's another thing you want to make sure about your mousetrap car is that it travels you want to make sure that it travels in a straight, not just a straight line, but the designated line. You want to make sure it does this and not this, because now you've traveled further, but only this distance here will matter. I'm going to measure this distance here. So if you're traveling this way, that's going to be a problem, especially in a hallway. The hallway in Farrell, if you go to the side too much, not only do you not get distance that you traveled, not only do you not get this distance traveled, you're going to run into the hallway wall. You're going to run to the wall there, and now you're getting friction against the wall, and you're not going to coast very far. So you want to make sure that you travel in a straight line. So it may be better to have 4 wheels instead of 3. But the thing about 3 wheels is that there's less kinetic friction here. So you're losing kinetic energy into this guy here. You're losing energy at this point here. With 4 wheels that you don't have to if you don't want to. And so what's going to happen is that on these 4 criteria, you'll be judged on those 4 criteria, and then you'll be ranked on those, and then the average ranking will dictate will be added to your score for the assignment here. And I'm going to have mine in there as well, and so ideally you will beat my car. The thing about my car, though, is that I'm trying to put as little effort into my car as possible, and so let's see here. I'm gonna pull up. There we are. We don't need to be sharing anything anymore. Stop sharing. There's the question, right? Yeah, there it is. Okay. Okay, so I try to put as little effort into this as possible to act as a, shall we say, a null hypothesis. Can you basically making a hypothesis for yourself? My car will do better than the professor's car, and so I try to put as little effort into this as possible. And it turns out that means that this is very light, and very light things tend to do very well. And so it was a bit of a problem. So I'm giving you a warning. You want to it's going to be a case of, can you do better than this guy? And it is possible. You want to go far, and so you want to take advantage of everything possible to make that happen. Is that wheel broken? Yeah. Hard to say. Whatever. The alternative ideas on what not to do. So here's an idea of what not to do. This car was turned in last year, and it did not very well at all. It was definitely very cheap because I believe, memory serves. I think I allowed students to use some dowel. Yeah, I got a little extra dowel from when I built mine, and so I think I allowed students to use that. And then, so we have here. These are medicine caps. These are caps off of medicine bottles here. So those are those are free because they come with the medicine, right? And I think I added just a little bit more to that there. What she had done was that she had instead of using dowels here, she had used she brought in with a cord of some sort or another, and so she was trying basically she was hoping to take this guy and twist on that cord, and it's like, well, cord doesn't transfer torques like that very well at all, and also she had secured the axles down with staples, and those staples all the way down, which means that this was a whole lot of extra friction. It's like, really? Anyhow, it did not go well for her on that day. I think we ran a little bit over on that, and so I had her make a few improvements to it, and then we tested it. It still didn't do very well. So there are some basic designs out there on the internet that will probably serve you quite well, and will make you make things that go quite far, because this is shall we say, a well-known problem to deal with, and so there's solutions on the internet. I would prefer it if you try to make up your own and do better than mine, and I think a few students actually did do that. So those are things you're going to run into. Those are the main big things you want to make sure you pay attention to. You want to get out as much force as possible, as quickly as possible, but you want to make sure that force does not exceed the force of friction, because that means that the force of friction, if the force out exceeds force of friction, that means you're not turning all of your potential energy into kinetic energy. You want to do it as quickly as possible so that you will coast as far as possible. It would be good to try to keep it as light as possible, but there's also some wisdom in making it heavier so that you can increase the amount of friction that you're putting out, and so that you can increase your force out. You want to make it as simple as you can so that you don't have so that you minimize the friction inside the system. Lubrication inside the system is a perfectly reasonable thing to do. There's the Boys or Scouting America, what used to be the Boy Scouts in America, has pinewood derbies, and so that is also kind of a solved problem, which means that they have developed a number of lubricants for pinewood derby cars so that the wheels turn round and round. If you want to, you are more than welcome to get graphite lubricant or Teflon lubricant and lubricate the mechanisms of your axles inside that you're holding on to. What else is out there? If you want to make your wheels really big and say use an LP, get a big old record, long play record, you're welcome to do that. Those tend to be collectible these days, which means that you better make sure that it's a duplicate that nobody cares about, because it's probably not come back to the source the same way as when it left, and they aren't easy to replace. Let's put it that way. But when I was in high school, Mr. Farden had kept a number of example mousetrap cars, and there were a few that had a non-zero, had two. I think there's at least one that had two LP records in the construction of the mousetrap car. I think that's about all the thoughts that I have on that. Did I talk about all the? Yeah, it's possible to score negative displacement, so make sure it always goes forwards. Um, Travel left and right will not be considered, so make sure it goes in a straight line when it goes. And the displacement score will be based on the average of 5 runs. And so, I believe in about a week, so next Friday. Right? Oh. In 2 Mondays. So let's see here. In 2 Mondays, that'll be the 16th. On the 16th, we will go. We'll go test our cars in Farrell Hall, level 1, and level 1 hallway there, in front of the professor, in front of the president's office, and who else is down there? President's office is down there, and across the hall, across the way from student council, whatever they want to call themselves. All right. Time is presently 54. I got this. Anything else I want to talk about really quick? Like, not in particular. Anyhow, questions? Make sense? Yes. So over the weekend you work on the design itself, and then you'll have a week to build it. No. You'll build it at home. Yep. You'll build it at home. I will continue lecturing. So tomorrow, on Monday, I have the design, and then you have a week to build it at home. It is possible. It is possible. You are permitted to build it at home, and then draft your design based off what you build by Monday. I think I had some non-zero number students do that, but that is, you don't have to do it that way. I am hoping that there will be a week's worth of opportunity for improvements and deviations from your initial design. When I initially designed this guy, I initially designed him with 2 wheels out front, which are the same size as this guy. You might notice that you might be able to see there. Yeah, you can see that the outside of this wheel here isn't exactly isn't a polygon like these guys back here. That's because it started out as one of these guys, and I cut him smaller with using a scroll saw. The scroll saw was not very happy about it because it tried to melt the plastic more than cut the plastic, which made for interesting results. Anyhow, and so I think I did technically dock myself for having changed out the design from 2 wheels in front of equal size to 1 wheel out front that's smaller. So I consider it as a happy accident that my the build plate in the 3D printer could only produce 3 wheels at a time instead of all 4, and so I was like, oh, you know what, 3 wheels is enough, and so I did not actually build my car to design spec, and I believe I technically penalized myself for that. But this time, having been more or less satisfied with my car, I will be, submitting my design as built rather than trying to build to something else. Any other questions? Hearing no further questions, I will see y'all's on Monday, assuming nothing weird happens.